Oh, it's getting.
Howdy!
Oh my gosh.
So I'm honored to introduce today's speaker of the distinguished lecture series of the Department of Physics and Astronomy, Professor Subir Sachdev. Subir is Herschel Smith Professor of Physics at Harvard University, and he specializes in condensed matter physics. Subir is well known for his research on quantum phase transitions and its applications to a variety of quantum materials, such as high-temperature superconductors. His research seeks to illuminate the boundary between the everyday world we live in and the subatomic world of quantum physics. Professor Sachdev is the recipient of many honors and awards. He recently was elected to the U.S. National Academy of Sciences. He was awarded the Direct Medal and the Lars Untitled Prize of the American Physical Society, among other things. So today, Professor Sachdev will tell us about two fascinating topics, strange metals and black holes, and how these topics are related.
No, I have a high tech.
Here's
Let's.
what's your name. So
Oh, thank you.
That's
Wow.
your name engraved.
My gosh, what an honor. by Mr. Laser himself. Thank you. Let's see. I have a fancy thing. Yeah, see there. You don't mind if I use that? Well, thank you very much, Katrina. It's a real pleasure and honor for me to be here, and actually my first trip to College Station, and it's great to meet all the people here, and I've learned a lot of interesting things. So I understand there's a fairly diverse audience, but please interrupt me, including the freshmen I just met. If I might tell you to well, sorry, I'm not going to answer the question, but at least I'll know where you are. All right, so as Katrin said, I'm going to talk about strange metals and black holes, and probably most of you don't know what a strange metal is, but just wait a few minutes, I'll define what it is. But let me just begin by telling you about ordinary metals, so something like copper or gold, which we certainly understand very well. So the defining feature of a metal, of course, for this lecture is anything that conducts electricity well, as copper and gold do. And the reason they conduct electricity so well is that in something like copper, the atoms all arrange in a regular crystal, but the outermost electrons, the valence electrons of copper, completely delocalize. So those electrons are able to move freely through the crystal. So to understand the property of a metal, we have to figure out how these electrons that are moving through the entire crystal interact with each other, and why do they then end up in a state that can conduct electricity so well. So this is a very difficult problem, you might think, because you would have to solve the equations of quantum mechanics for 10 to the power 23 particles. But nevertheless, we understand the properties of copper very well. I can predict in detail not just the properties of copper, but semiconductors, insulators, magnets, superconductors, and many other materials. And that's been one of the great successes in physics for the last 30 years or so. And the basis of this success is a very simple idea, which I'll try to illustrate now. I'm just getting used to this mouse. So this is the starting point of the theory of ordinary metals. So you have a bunch of electrons which are moving through the entire crystal. So let's imagine they're in some plane wave states. So as a function of the momentum, they have an energy that has some shape. And I've drawn the energy levels as discrete because imagine the metal is a big box, and so there's some quantization condition of the energy levels, although they're very closely spaced. So now what you want to do at low temperatures is occupy the lowest energy state up to an energy called the Fermi level. Now, one reason a metal is quantum mechanical is that this Fermi energy is actually very large. It may be 100,000 Kelvin. So at room temperature, you're actually at very low temperatures. These electrons are pretty close to their absolute zero of temperature, and so you do have to think about them quantum mechanically. We can't think of them as classical billiard balls moving around. Okay, so this is roughly then a very simple picture of the ground state. So now if you raise the temperature a little bit, these electrons will go into excited states and leave behind vacancies, which we call holes. So there's an excited electron here, and a vacancy here called a hole. And these will start to move around. And as they move around, they will affect the other particles. And so really the problem before us when you say driving some current in a piece of metal is how do all these pieces of these electrons interact with each other. So that's not an easy problem, but the solution turns out to be almost laughably simple, if you wish, once you understand how it works, is that you basically almost ignore the interaction between the electrons. And the reason we can get away with this, what would seem like a ridiculous approximation, is the idea of a quasi-particle. So the electron I showed you before was just one particle moving on its own. But what happens in a metal, ultimately, is that electron has a cloud around it of various other quasi-particle, of particle and hole excitations. But that cloud basically behaves like a lump, which for all practical purposes is a particle. It's a renormalized particle, if you wish. So it's got a mass, it's got a charge, it's got a spin, and the charge and the spin are the same as the charge of the electron. The mass may be slightly different. But once this happens, once you go from the real particle way of talking about things to the quasi-particle way of talking about things, then at low temperatures, you can just treat the quasi-particle as free, as moving essentially on its own, except when very rarely it encounters another quasi-particle. So that separation that you can first renormalize the bare electron into a quasi-electron while ignoring anything else, and then worry about the interaction between the quasi-electrons. That's really the magic tool that's responsible for essentially all of the successes of condensed matter physics, as it's called. So here's a list of successes that some of you will recognize, and other of you probably just don't worry about it while I'm showing this slide. But as I mentioned, this idea of quasi-particles is the reason for the success for the theory of metals, insulators, semiconductors, theory of superconductivity in the presence of disorder, metals in lower dimensions, and also exotic phenomena called the fractional quantum Hall effect. So the fractional quantum Hall effect is somewhat more different in the sense that the quasi-particle does not have the same quantum numbers as an electron. Its charge can be a fraction of the charge of an electron. It has 1/3 the charge in the most famous state. But nevertheless, it's some particle. So once you understand how this fractional charge forms, you can just treat it like any other particle. So and this basic tool is really, it's so ubiquitous in condensed matter physics that people don't even mention it, or in some cases don't even realize that you're making this assumption. Okay, so with that long introduction, now I want to talk about materials where this all-powerful idea seems to completely fail. And it fails most spectacularly in the high-temperature superconductor. So here's a picture of a high-temperature superconductor. It's a crystal of yttrium, barium, copper oxide as an example. I won't go any of the details of the complicated phase diagram of this material as a function of temperature and density of carriers, which is controlled by changing the relative composition of the elements. That's really more than a course in itself, and I only have a little time. So I just say two things about these materials. One is that they're high-temperature superconductor, meaning in this blue region labeled SC, they conduct electricity at zero resistance, up to a temperature as high as 100 Kelvin for this particular composition. Other materials an even higher temperature. But when you go above this TC, especially at the highest TC, you go up here, then you get this phase of matter that now some people anyway call the strange metal. I'll just mention some of its properties, not all of it. It's been the subject of much work in the last 2 decades. And every one of them looks different from what we are accustomed to in a metal like copper or gold. And so much effort has been expended in trying to understand this strange metal, and I'll tell you about some recent ideas and their unexpected connections to other fields of physics. Right, and one of the reasons we are obsessing about this, well, for one, we're bothered by the fact that our methods fail completely, but also, for more practically, if you want to make a better superconductor, if you want to raise TC, we're not going to be able to do that unless we understand what we are fighting against. we're fighting against a strange metal on the other side. So really need to understand both sides of this point if you have a hope of any complete theory of what the value of the critical temperature is. Okay. So this strange metal, as I said, is called strange, but other people call it bad and other people call it incoherent. These are technical terms, not pejorative terms. And what do they, why do we have all these names? Well, it's strange, well, because it doesn't look like an ordinary metal. And one of the ways it doesn't look like an ordinary metal, that the resistance, as you increase the temperature, is proportional to temperature. So let me explain why that's a bit strange. So metal is, in all metals, as you raise the temperature, the resistance goes up. So as you're increasing the temperature, these mobile electrons start colliding with each other, and that increases the resistance. On the other hand, if you have an insulator, like diamond, at 0 temperature, diamond is a perfect insulator, so resistance is infinity. But as you raise the temperature, you create vacancies, particles and holes, which can start moving around, and so the resistance goes down. So when the resistance goes down as you raise the temperature, that's typical of an insulator. If it goes up, it's typical of a metal. So this looks like a metal with the resistance that's going up. But in almost all other metals, the resistance goes as the second power of temperature in the regime where you're dominated by electron-electron interactions. And here it seems to be the first power. So that's one major mystery. The other, even deeper mystery in some sense, is the resistance is very large. So even though, but it's not an insulator because the resistance is going up as you increase the temperature. But what do I mean by very large? Well, it turns out there's a fundamental unit of resistance in 2 dimensions. It's slightly more complicated in 3 dimensions, but not much more, which is just given by constants of nature, universal constants of nature, which are Planck's constant and the charge of an electron. So some of you may know about the quantum Hall effect, where there's a quantized conductivity, which is in units of E squared over H. So E squared over H is unit of conductance, H over E squared is unit of resistance. It's about 27 kilo ohms. And this resistance being much larger than H over E squared, in a typical metal, if you had a metal with such a large resistance, it would become an insulator. There'd be so many impurities that the electrons will not be able to move freely at all. They would localize. So you have a metal which has a very large resistance, which is increasing as a function of temperature. So that's the mystery of the strange metal. Okay, so now I'm going to try to resolve this mystery by telling you about some simple models, at least some simple models that can display this behavior. But before I do that, I need to define for you a little better what is a quasi-particle. Oh, forget that. Okay, that was a joke I forgot about. Another thing I forgot. So here's another material, the so-called pnictide materials, where again you have the same property of a resistance of linear temperature and much bigger than H over E squared. Okay, so what is a quasi-particle? Well, another way, more abstractly to think about a quasi-particle is that a quasi-particle excitation is something that can be combined with a radioactive excitation to create a new excitation. I could have a particle here and a particle here, and if they're both excitations, I can have an excitation where I create them both. And in a many-body system, it's not obvious you can do that because everything is interacting with everything else. But if you can do that, well, that means that your system has quasi-particles. So if I have a system of n particles, say on each side, I have a lattice with n sides. On each side, there can be a particle or not, or it can be a particle spin up or spin down. Let's consider the simplest case where they don't have a spin. And the total number of states is 2 to the n, which is exponentially large in n. And remember, n is 10 to the 23. So that's really an unimaginably large number. That's how many quantum states I need to describe. But the number of single states for a single particle in a system of n sites is still n. It's not 2 to the n, it's n, which is a much smaller number. So the number of possible energies for a single particle or a quasi-particle is epsilon alpha, where alpha goes from 1 through n. Now, a given state alpha could be occupied or not, and that I can describe by this binary number, n, that is either 0 or 1, hence of alpha. So the total energy of the system above the ground state is the sum of the energy of the quasi-particles. And the quasi-particles could interact with each other, 2-body interactions, free body, and so on. But we don't take this expansion too far. And now the point is that on the left-hand side, I have 2 to the n numbers because I have 2 to the n choices for n alpha. And on the right-hand side, I have only polynomial in n numbers, which are epsilon alpha, f alpha beta, and so on. So we have this remarkable feat in a system with quasi-particles that you can describe exponentially large number of levels with a polynomial number of parameters. When you put it that way, just the fact that quasi-particle exists seems quite surprising. And almost always this works, but sometimes it fails. Okay, so that's one defining property of a system with quasi-particle. Another defining property is the following. It's a dynamical question. If I take a metal and I kick it at one point or in some large region, I'm injecting some energy into the region that will create some quasi-particles. They'll start moving around. Eventually they'll hit each other and quickly come into equilibrium. So this was a process that Boltzmann already understood in the 19th century. He wrote down the famous Boltzmann Equation, which tells you what would happen, for example, if you took all the molecules of the gas in this room and put them in the corner, the gas will quickly expand and become uniform and come to and look like it's in equilibrium very quickly at some temperature. And how that happens is something Boltzmann Equation describes. So basically what Boltzmann realized is it takes a few collisions between the classical particles to reach a thermal state. You can apply Boltzmann arguments almost unchanged to even this complicated quantum system. The only difference is that you have to worry about the Fermi exclusion principle. And so as a result, when you work it out and you ask how long does it take for a system of quasi-particles to come to equilibrium, this tau equilibrium, you get a number that looks like this as the temperature goes to 0. So here I just want you to notice that as temperature goes to 0, it diverges as 1 over temperature squared. And as we'll see, this is a long time as temperature, it diverges, so it's very long, but long compared to what I haven't quite explained. But just remember this 1 over temperature squared behavior as characteristic of a Fermi liquid or an ordinary metal is how long it takes for it to effectively lose memory of its initial state. Okay. All right, so now I want to move towards systems that for which the quasi-particle system doesn't work, description doesn't work. So here's one attempt, which will eventually succeed, but in a not very satisfying way. And it's historically how we started to first understand such systems. So we take a system of qubits. So in real life, you could take a crystal like cobalt niobate, and it turns out each cobalt, this is an insulator, so we don't have to worry about moving electrons. But it turns out each cobalt ion has 2 possible spin states, which are just labeled up and down. Okay, and they're coupled to each other, and you can also then apply a magnetic field in a transverse direction, as it's called, which will flip these spins. So I introduce these Pauli operators, sigma z and sigma x. Sigma z measures whether it's up or down, and sigma x flips the spin. And then the effective, the Hamiltonian that in real life also describes this cobalt niobate is this very simple Hamiltonian called the Ising chain in a transverse field, where you have near neighbor spins have a sigma z interaction, which tells you that they both want to be parallel to each other, because if they're both parallel, this number is positive. And this is G is the transverse field, which flips the spin. So as a mathematical problem, I can try to understand the low energy state of this Hamiltonian. And what you'd conclude is when G is 0, then the spins want to be either parallel or all up or all down, which we call a ferromagnet for obvious reason. That's what happens in a ferromagnet. On the other hand, if the G is very large, there's a unique state where the spins all point to the right. And remember, the right pointing spins are up plus down, and the left pointing spins are up minus down. And this would be the unique ground state. So what we notice here is that as a function of G, between these 2 limits, there's a dramatic change in the ground state. You go from having a ferromagnetic state with a 2-fold degeneracy to a unique paramagnetic state. And so there must be what we call a phase transition, a quantum phase transition between them. So as you vary little g and also introduce a temperature axis here, this is what the phase diagram ends up looking like. So when you're on the ferromagnetic side and you raise the temperature a little bit, you get some excitations. And the excitations are these domain walls between up and down spin. And each domain wall then looks like a particle. It'll move around, and there's your quasi-particle. So we're trying to destroy quasi-particles, but there it is. On the other side instead, the spins all point to the right, but there's a few excitations that point to the left, and now the left pointing spin is a quasi-particle. So both over this side and that side, you do get a quasi-particle description because it just looks like little lumps that are moving around. So you might think in between maybe all hell will break loose and you won't have quasi-particles in the red region. Turns out you don't quite succeed, and that's because of some magic that happens. This system of spins, which are essentially bosons, ends up having a representation which is just free quasi-particles, provided you write it in terms of fermions. So I'm not going to describe that here, but it's a rather special set of magic that's very special to one dimension, and it happens quite generically in many one-dimensional models at low temperatures. So anyway, so we succeed. We try to destroy the quasi-particle by studying a quantum phase transition at GC, and in one dimension we fail. So let's go to one higher dimension on a square lattice. So I'm not showing you. There are recent experiments studying this model on the square lattice, but it's still too preliminary for me to show here. But this is the theoretical phase diagram we expect. So you have a ferromagnet and a paramagnet, just as I said. And then in this intermediate region, which I'm now calling quantum critical, indeed, our hope succeeds. We do find a regime where quasi-particles don't exist. And you see this kind of fan-shaped intermediate region is very similar to what the experiments are looking like, although this is a very, very different system. The downside is the theory of this region is extremely difficult. This particular point was first understood by Wilson and Fisher, and in today's language we call it a conformal field theory. And what Wilson and Fisher were studying was the Curie transition of Ising spins at finite temperature. So they were considering a three-dimensional classical system at finite temperature. It turns out there's this magic mapping between classical systems in 3 dimensions and quantum systems in 2 dimensions, because you can think of one dimension as just the time dimension. So what they were secretly studying was the 2-dimensional Ising model in a transverse field as a quantum system. And in that language, you would say that what they discovered was what we call today a conformal field theory, which is a very special field theoretical object with lots of symmetries and strongly interacting, but extremely difficult to work with. Nevertheless, just from the structure of this solution and various calculations that are described at length in many papers that I and others have written, we came to the conclusion that if we ask the following question, that how long will this system take to equilibrate if I kicked it a little bit? When the blue regions, it turns out it takes quite a long time, but the fastest possible equilibration appears in the central quantum critical region, and it turns out to be this remarkable universal result. It's the tau equilibration now only depends on the temperature and Planck's constant. Forget about KB, that's just a converging temperature to units of energy. That's just a question of what units you use. This hashtag is a pure number like 5 or 2.7. We don't actually, but strangely enough, we don't know this value because it's really difficult to compute. But we know it must be of this form. And so we find that it equilibrates in this time about a 1 over temperature with no constants here. So for example, if I took 2 different materials, cobalt niobate and some other material, they have completely different interactions and the values could be very different. But it turns out that this result is independent of what the interactions are. As long as you're at the critical point, it just goes as 1 over temperature. So that's really some ways quite surprising. And also notable is that this time is very short compared to other times we saw. In particular, as temperature goes to 0, this goes as 1 over temperature, whereas in a metal we saw 1 over temperature squared. So this is a much shorter time, and that's another thing I want you to remember. All right, so that's the end of that story. And perhaps some of you got lost in this last transparency if you haven't met conformal field theories before. But this historically was the first place we met and started to grapple with a system and make some progress with a system that has no quasi-particle excitation. So now I'll tell you about another system, which turns out was discovered quite a while back, but there's been a rapid progress in the last few years, and we are starting to learn much more about the dynamics of system without quasi-particle. So before I tell you about that system, let me tell you about a system with quasi-particles. Very, almost a trivial model of a metal that has even no sense of space. So here's what we do. We take endpoints placed randomly in space, and maybe we fill half of them with electrons. Okay, and now we allow these electrons to move, quantum mechanically, of course, and we just let them move randomly from anywhere to anywhere. So this electron can hop from there to there, and so on. Just pick any electron, and it's just going to move anywhere it wants. So every one of these processes has some amplitude, or a tunneling amplitude that is say quantum mechanics, which has some number. So there's some number associated with each one of those steps. What number do we assign? I don't care. Pick a random number. So you pick basically n squared random numbers for any pair of points. Okay. So that's this model, and the only thing, other thing we need to know that these are fermions. So if you have a loop, you pick up a minus sign, and they obey the exclusion principle. All right, so this problem is easy to solve. For those of you who are mathematically inclined, there's a mathematical way to write it. These n squared random numbers are these Tij. For an electron, go from side j to side I. And the way you solve it is you just take this matrix, Tij, this n by n matrix, and diagonalize it. All you need to know is something about the Eigen States of a n by n random matrix with random entries. And we happen to know a lot about that. There's books written on that topic. So for example, there's a bunch of energy levels with some spacing about a 1 over n. Their density of states, or the number of levels per unit energy, has a semicircular form. So you pick some Fermi energy, you occupy all the levels here, you leave these empty, and that's your ground state. And clearly, since these are free electrons, they don't see each other than occupying or not occupying levels, a quasi-particle description works. But just to make that point, let me show you, think of the system in a many-body way. So here what I've done is a very simple calculation on my laptop. I took a 12 by 12 matrix, N, so I just had 12 sites. And I found it, took random numbers for its entries and found its eigenvalues. So the set of all many particle states are 2 to the 12, which is 4096. And I get those by just setting these n alpha to be either 0 or 1. And E alpha there are the 12 random eigenvalues. So what I've shown you here are the 4096 levels. I could easily do this for many more levels, but it'd be hard to draw on this picture. So what do I want to emphasize? First of all, the spacing between these levels is 2 to the minus n, because there's 2 to the n levels in a region of width n. I mean, I don't care about prefactors in front of the exponent. So they're very tightly spaced. What this means is I go from one level to the next, the set of n alpha changes completely. Because the spacing between the epsilon alpha is 1 over n. The space, and so to get something really close, much closer than the epsilon alpha, I have to pick some other set of epsilon alpha, which accidentally happens to be very close to the other one. Okay. But one very curious thing is that at the bottom of the band, it's completely different. The very lowest energy levels are very different, and you can see they're much less dense here. Why is that? Well, you have these levels spacing 1 over n. So everything in the green region is occupied. Those are empty in the ground state. Then to create an excitation, what I have to take is to take the last occupied level below the Fermi level and move it up. That'll cost me energy 1 over n. I have no choice. I can't move anything else up. It's just not allowed by the Fermi exclusion principle. So that's why the spacing here is 1 over n. And that's a huge signal that the energy levels obey this very simple quasi-particle form. All right, so many of you probably getting bored. So now let's get to something more interesting. Everybody knows that, right? So now take the same set of 12 sites and put n, fill half of them. And now allow the electrons to move, but don't allow any electron to move by itself. It has to pick a partner. So for example, those 2 electrons can move. But one thing important is nothing special. Each electron is constantly changing partners. It's not as if they're paired in any way. So another pair can move and another pair can move. So there's only pairwise motion, and the pairs are instantly forgotten. Each electron is free to pick another pair the next time it moves. And that's it. So that's the model. And what's happening here is this model is leading to what we call, in today's language, entanglement. Every electron, every time it moves, it's getting entangled with another electron. And it's quantum mechanically interfering with all the possible sets of pairs of electrons. So that's the model. And this turns out to be, in many ways, both a model, as I'll show you, of a strange metal and also a black hole. And that's going to be the second part of my talk, where there's no clock here. So somebody's going to have to keep me on time. So I end at 5, right? Okay, I'll ask. All right, so here's the mathematical form of it, but really the pictures say everything. Oops. Just imagine these moving in pairs. And if you want to see something more precise, here's the form where you go for electrons in site K and L can go to site I and J. And there's some random number associated with that process is UIJKL or just random numbers. Okay, so this model, which is called the SYK model due to the references shown here, for this model now, let me do exactly the same thing I did for the simple model. I take 12 sites and I find all the energy levels. Now here, I can't just get away with diagonalizing a 12 by 12 matrix. I have to diagonalize a 2 to the 12 by 2 to the 12 matrix, a much harder job. So here, even the best computers in the world couldn't do it for n bigger than 40. Okay, I just did for 12. And you would get, 2 to the 40 levels. Even in the previous case, you would. And here's, for 12, a plot of all the levels. So just as before, the spacing is 2 to the minus n in the middle of the spectrum. But remember, we can go down at the bottom of the spectrum and look at what's happening here. Well, it turns out, and it's not so clear from this very small value of n that I've used here, the spacing here is much smaller than the middle of the band, but it's much smaller than the middle of the band, but it's also much smaller than the spacing in the bottom of the band in the quasi-particle case. It's not 1 over n, it's still exponentially small. And this number S naught, as we'll see in a while, that's related to the Bekenstein-Hawking entropy, is something that we computed a while back. It's a transcendental number that I'm very proud of, which has been numerically verified by studies of energy levels like this. And this particular fact that the spacing here is exponentially small, but still larger than this spacing because S naught is smaller than log 2, is basically evidence there are no quasi-particles. Because if there were quasi-particles, by definition, the spacing should be 1 over n. All right, so that's one piece of evidence. Now, in the past 20 plus years that this model has been studied, we know a lot about this model in the large n limit. Among the things we know is, okay, here's getting a bit technical, but just for one slide, the Green's function behaves as 1 over square root of temperature time of the fermions rather than 1 over time as we would do for a system with quasi-particle. And then at finite temperature, the Green's function has this conformal form. And from this, we come to the main point, the other way of thinking about quasi-particles. So remember, I defined quasi-particles 2 ways. One was that there's energy is the sum of quasi-particle energies plus interactions. And the other was the equilibration time is 1 over temperature squared. So what is the equilibration time here? Well, that turns out to be not 1 over temperature squared, but again, this universal number, which is completely independent of all the ui, j, k, l, which we h bar over kt. Planck's constant divided by temperature. Sometimes people call this the Planckian time. Okay. So that's, again, the other smoking gun signal that this is a system without quasi-particle. So we have met two systems now which don't have quasi-particle. The Ising model at its critical point in 2 dimensions, and it only 2. If you go to 3 or 4 or 1, it doesn't work. 2 is special there. Or this SYK model. The energy is not the sum of cannot be written in this form. And secondly, in both systems, we found this magic time, this very rapid time of very short time of h bar over t, and all others in the quasi-particle system had a much longer time. Okay, so this thinking in this way led me to conjecture that maybe this is the smallest possible time. That is, if you have a system with quasi-particles, by definition, it's going to be slow in equilibrating because each quasi-particle likes to live around for a while. If you don't have anything to live around, it's just some quantum soup, and that's going to very quickly entangle with each other. It won't look like individual lumps, and therefore it should thermalize very, very quickly. So perhaps for any system, if you look at its equilibration time, it should be greater than some constant times Planck's constant divided by temperature. All right, so this means that there's kind of a speed limit for systems to thermalize. You can't make it thermalize faster than Planck's constant divided by temperature. Just to see that this is quite surprising, consider a classical system. If you took a classical system where h bar goes to 0, this bound says that tau equilibrium can become as small as you want for a classical system. And that's true. If I have a bunch of springs and I kick it, and they're nonlinear effects, they will eventually thermalize and become some thermal gas of oscillations. And if I just scale up all the springs by a factor of 100, every spring will vibrate 100 times faster, and the system will thermalize 100 times faster. So I can make it as quick as I want, just by having very rapid oscillators. Now what happens quantum mechanically with something very rapid oscillator? It doesn't thermalize, it goes into a ground state and has a gap to all the excited states. So in effect, that rapid oscillator just disappears from the problem because it doesn't want to be excited to that very high energy state. It's got a huge gap near it. So quantum mechanics is much more subtle because of the discreteness of energy levels. The things start to equilibrate and thermalize very, very quickly, only if they happen to be a very special system where you cannot create separate lumps of excitations. And for such systems, this seems to be the fastest possible rate. Okay. Yes. Yes. I mean, unique, or there's no ground state entropy. There's a 0 temperature entropy, but there's no ground state entropy. It's a question of orders of limit of n goes to infinity and t goes to 0. So what I was discussing, to define the entropy, that means I send n to infinity first and then temperature to 0. Then there's a finite entropy. But if I just look at the ground state at any finite n, there's no degeneracy. Yeah, but this is, for example, like the ice model of Pauling. That's very different. There is a ground state degeneracy, and it's very fine-tuned. This is not fine-tuned. This is actually very robust. For any random interaction, you get this behavior. Okay. So here I just want to return back to the strange metal problem and tell you about some recent and not so recent work by my colleagues who are starting to connect this SYK model to actual observations. So this is a toy model, but still what I regard it as quite an important step. So what I do is I take the model I've just described and consider it as a big atom. So here's an atom which has got n orbitals. And this atom in isolation is what I described so far. And I take a lattice of these multi-orbital atoms, and now I allow electrons to hop singly from one atom to the next with the hopping amplitude t. So here's is written out in equation if you want to see it. So what we know is that if you allow electrons to hop one by one, as I showed you, you do get quasi-particles. On the other hand, if the electrons only move 2 by 2, as inside this atom, you don't have quasi-particles. So now looking at this model, you would say, at low enough energies, the one by one process is always going to win, and this should have quasi-particles. So then you ask the question, how low in energy should you go? Your first guess would be, you just go at energy, at temperature smaller than little t, this thing should just look like a plain old boring metal. Turns out that's not right. It does look like a plain old boring metal, but only at a temperature much, much smaller, t squared over u. You can make that very small by making u large. And above this temperature, so here's E sub c, and above this temperature, we have just what the doctor ordered. We get a resistance, which is linear in temperature, which is much larger than h over E squared, and it's increasing with temperature naturally. So that's really the first model where you have, you can essentially establish the existence of a non-quasi-particle strange metal. And what's happening here very roughly is that each little dot is decohering the electrons, if you wish, making an incoherent soup without quasi-particles. And then most of the hopping just happens incoherently between these dots. But things do move, and eventually the motion takes over and it becomes a Fermi liquid, but only at very low temperatures. All right. So that's actually concludes what I have to say about strange metals, and now I want to talk about black holes. So now I need to know how much time I have. 4:43. Okay, plenty of time. Is there? Okay, well, I can't see it. Oh, there. Yes. Any questions then? Only one or two. Okay, then everybody's with me, right? Oh. Yes, please. Well, at the moment, at the moment, I'm just talking about this model, and not I take UIJKL and TIJ just random numbers. I am not, for this model, I'm not tuning anything. It could be anywhere. I take the average value U, this U to be much larger than T. That's the only constraint. For this model, this is quite generic behavior. Well, I'm looking at temperatures between, so this is critical at temperatures bigger than EC and smaller than U. So I'm in that window. Yeah. Okay, I should move on, yes. Well, it's simply because it's something like an orthogonality catastrophe, because you have decoherence locally. The matrix element for hopping is actually renormalized down because of that. I should also say the fact that it's linear in temperature is by far not a trivial thing. It's not due to some Bose factor in the classical limit. It really relies on this 1 over square root of time behavior of the Green's function. It's crucially connected to that. All right, now let me move on to black holes. So I have 15 minutes or even less. I can't teach you about, I myself don't, but what I know about black holes can be said in 15 minutes, so that's the lucky part. So black holes were objects discovered solutions of Einstein's equation first, and for a long time they were thought to be just figments of imagination, but now we know that they're everywhere in the universe. There's a supermassive black hole at the center of every galaxy, including our galaxy. And they're objects that are so heavy and so dense that light cannot escape from them. So these are things everyone should know. The other chapter in the history of black holes was some very brilliant work in the mid-70s by Bekenstein and then Hawking on thinking about the effects of quantum theory on these remarkable astrophysical objects. I mean, at that time, I don't think Hawking, we weren't aware that there were any black holes in the universe. There wasn't any well-established example, but they nevertheless started thinking about them. And so what Hawking concluded, that once any black hole, which which Einstein's equation says no light that ever goes in ever comes out. So it's just a featureless black object in the universe where it has no properties other than the fact it's a sphere and it's black. Actually is teeming with lots of excitations. It's radiating energy, and it's eventually it'll evaporate like a cup of coffee. And as it's evaporating, it has a temperature. So there's lots of quantum fluctuations on the horizon. Roughly speaking, if you know a little bit about entanglement, you can think about, some quantum fluctuation where a positron falls into the black hole and the electron comes out. And so these positron and electron are forever entangled with each other. But since the other positron is forgotten inside the black hole, to the outside observer, it looks like the black hole has an entropy. Anyway, so it's got a temperature and entropy. So this is all I have to say about it. But despite these rather vague arguments that I presented, Hawking did a very precise calculation of actually the value of the entropy and the value of the temperature. So I'll call these the Hawking temperature TH. I'll show you its value in a minute. But the even more surprising result of Hawking was the entropy is proportional to the surface area of the black hole. And anything else in our universe, a cup of coffee, the entropy is proportional to the volume of that material. But black holes seem to be very different. The entropy is proportional to the surface area, not the volume. And roughly speaking, this is because this picture of entanglement across the horizon, that's where the temperature comes. It's happening only near the horizon, where you're able to entangle with degrees of freedom on the opposite sides and never see them again. And it's because of the importance of the horizon and this entropy, you might think, that's roughly how you could imagine, reconcile it to your intuition of why this strange thing happens. Okay, so these are two basic properties of black holes, but let me show you one other crucial property, which at some sense was also known to Hawking. And that has to do with what's called the ring down time. So this is the picture of the famous LIGO observation of two binary black holes merging into a single black hole. And this happened in a fraction of a second, billions of light years ago, which was then observed last 2 years ago. So here I want to focus on the very large stage. So in classical general relativity, there's this pair of black holes, and it's oscillating, and then very quickly it's a perfect sphere, and then forever it's sitting as a sphere with nothing. It's totally featureless. It's just a unique state sitting there forever. So you can then ask, well, how did this black hole die? How long did it take for this last step? So there's some exponential decay for this very last step. This you can compute from Einstein's equations, and you find it's 8 pi gm over c cubed, which is 8 milliseconds for this particular black hole of 60 solar masses. Okay. Now, if I take the Hawking point of view, Hawking says, no, this black hole is not a featureless object. It's a strongly interacting quantum system of some type with an entropy and a temperature. Okay. So then, historically, I could come and say, okay, if it's a strongly interacting quantum system, the fastest possible way it could possibly equilibrate is h bar divided by Planck's temperature. That's what I've been talking about all along. Okay, so you can go in and then look at the value of h bar over Hawking temperature, and you find it's exactly this time. And this tells you what the Hawking temperature is, which Hawking computed. So this is the key connection really between absence of quasi-particle quantum system and black holes. They both are systems, quantum systems that equilibrate as fast as possible. What this tells you, if you're going to equate black holes to quantum system, the black hole is like a quantum system without quasi-particle. It doesn't tell you the converse, that every system without quasi-particle is a black hole. But many that we're understanding better are. And so now let me try to give you that part of the equation. Which quantum systems are like black holes? Okay. So these are the three main properties. This is all I need to know about black holes. They have a temperature, they have an entropy, and they relax to equilibrium in h bar over the temperature. I don't even need to, in fact, this result is far more universal than the Einstein result. It's true for basically every black hole that's ever been studied in any space-time. Okay. All right. So now the connection between black holes and quantum system. So the first example of this connection appeared in something called the ADS-CFT correspondence that was discovered in string theory, especially by Maldacena. So I can't do much here on that, other than just tell you a little bit about what the result is. So what Maldacena studied was a conformal field theory, as an example, in 2+1 dimensions. So this is very much like the Ising model I gave you. That's also a conformal field theory. But Maldacena studied a different conformal field theory, which had this very special property called supersymmetry. And from our point of view, that's just some higher degree of supersymmetry that allows you to make progress, even in the strongly coupled regime. Other than that, it doesn't seem to really modify any basic property of the system, of a generic quantum field theory, conformal field theory. All right, so this conformal field theory is 2 space and 1 time dimensions, and I'm showing the 2 space x and y right here. So imagine this particular theory. Just think of Ising spins are sitting on this plane right here. So these Ising spins are sitting here. These qubits are sitting on this plane, but they have very special set of interactions that make them realize this maximally supersymmetric conformal field theory. So the amazing result of Maldacena was that this theory, in a particular limit, is in fact a theory of gravity. But that theory of gravity lives not in 2 space dimensions. It lives in 3 space dimensions. So that's called the emergent direction, which is R. So now I have a theory in a space called anti-de Sitter space in 4. The 4 stands for 3 space. That's R, X, and Y, and time, which I'm not showing. And the metric in this space, this is the metric of anti-de Sitter space. And it's also quite easy to understand. So this metric is a pure Lorentzian metric in 3 space and 1 time. So X, Y, and R and 1 time. That's just Minkowski space. But all you do is you make Minkowski space shrink by a factor of 1 over R squared. So as R increases, the space shrinks, and that's what's shown by this picture. Okay? So what Maldacena showed was that, again, I'm paraphrasing and simplifying here a little bit, that a theory of gravity, if I took a theory of gravity in this, as a quantum theory, in this 4-dimensional space-time, which is curved, in fact, if I just took Einstein's theory, so this is the Einstein-Hilbert action, R, and this is the cosmological constant, the famous mistake of Einstein. So in our universe, this is a very, very tiny positive number. But here you have to take it to be a large and negative number. This is the negative cosmological constant in some convention. So this, essentially Einstein gravity, if you quantize it, it's equivalent, this 4-dimensional Einstein gravity is equivalent to this quantum system in 3 dimensions, 3 space-time dimensions. So that's, so far it's a mysterious assertion, but now I want to show you that once you accept this assertion, the mysterious properties of black holes suddenly start to make sense. The 3 properties I emphasized, so these are the 3 properties if you want to remember, these 3 properties. Okay, so how do we understand these 3 properties once you accept the Maldacena duality? Well, first of all, there's an extension of this duality. So here I should have also mentioned this correspondence only holds at 0 temperature. So I'm assuming the boundary, this theory, which I'm going to call the boundary theory, is at 0 temperature. So now let me raise the temperature a bit. So I take the boundary theory and make it at some temperature. Well, what happens then, in this emergent direction R, you get a black hole. This is the black hole horizon at some distance, capital R, from the boundary. And this is the connection between the temperature and that. It's again only involves Planck's constant, and you convert temperature to this distance. This is the metric, so it doesn't matter. So there's a black hole horizon here, which is extending over all x and y directions. Okay. Now once you accept this, suddenly all the properties of black holes make sense. Well, so Maldacena says this theory of gravity with the black hole, all of the space-time is equivalent to this theory. Well, this theory has this boundary theory has an entropy. It's just an ordinary bunch of qubits in 2 dimensions, has an entropy. Therefore, this also has an entropy. So that's property 1. Secondly, the entropy of the black hole, we learned, was proportional to the area. Well, if this theory is the same as this theory, no surprise here. Of course, the entropy is proportional to the area. The system is 2-dimensional. So that's why this emergent direction is essential. What's a surprise, and what looks surprising here, that a theory of gravity has entropy proportional to the area, becomes completely natural because it's proportional theory on the boundary. All right, so that's pretty much it. And then finally, if I come in and kick this theory and ask how long does it take to equilibrate? Well, I just told you there were general arguments in any conformal theory. That's a time of order h bar over kt. So if I kick this theory, what do I have to do? I just have to redo the calculation in Einstein's equation. And I just showed you, or I asserted from Hawking's calculation, that's exactly h bar over Hawking's temperature. So all the 3 basic properties of black holes are immediately understood by this duality. Okay. All right, so then let me just finish with this point. So let's put the 2 together. So I told you about the Syk model, which is this model of pairs of electrons on n sites. Is this dual to some theory of gravity? You can ask, okay. All right, well, I wouldn't be asking the question, and the answer was no. Now we know, but at the time we wrote this model, this was not even a dream in my wildest imagination. We were studying it for a long time, and around 2011, I started realizing that it's actually, after everything I learned from Maldacena, that this actually, in fact, could be a theory of gravity. And what theory of gravity it is? Well, it's almost the same as Einstein theory, which is this R plus 6L squared. All you got to do is add electromagnetism. So it's a black hole in Einstein-Maxwell theory, not just Einstein theory. So here what I've done is I've taken the Syk model, which lives at a point really, but imagine it has some width. So I'll put it in 2 dimensions. So this T2 means this direction is finite. It's a torus. That's what the T2 means, a 2-dimensional torus, the surface of a donut. I put this on the surface of a donut. Then the black hole horizon is also the surface of a donut. And if you now solve the equations of Maxwell-Einstein equations, for the case where you smear some net charge density on the boundary, Q, then you create an electric field and by Gauss's law, and that electric field will distort the curvature of space-time, as you can determine from solving Einstein-Maxwell's equations. And what you find when you solve Einstein-Maxwell's equation is that right near the horizon, the metric looks 2-dimensional. In other words, this finite dimension T2 basically shrinks to a point, so you can forget about it. And now this is a theory in 1 space and 1 time dimension. And in fact, it turns out to be precisely anti-de Sitter space 2 rather than anti-de Sitter space 4. The theory in 1 space and 1 time, and it's dual to a theory in 0 space, because this is basically a point on a donut, and 1 time. So it's again the same dimensionality correspondence as in Maldacena theory, but now this is actually much simpler. So this is something I conjectured in 2010, and some brilliant work of Kitaev and Maldacena and Stanford and others have pretty much proven that the low energy dual of this theory is a theory of gravity on this anti-de Sitter space. And the way I reached this conjecture was just by matching properties. I look at all the properties of this black hole, compare it to all the properties that we know of the Syk model, most importantly, this h bar over t quantum time. All right, I think that's all I have. Oh, I'm over in time and over. I can just, so there's a lot of work on something called many-body quantum chaos. I feel I should very quickly mention it because it's what's happening these days. And also to mention the names of Steve Schenker, Douglas Stanford, and Juan Maldacena, who have, by a slightly different time, not this equilibration time, but something they call the Lyapunov time, have proven many things, like a rigorous lower bound and the maximal fastest possible Lyapunov time, which is reached by both the Syk model, Einstein gravity, and supersymmetric Yang-Mills theory. So let me conclude. I've told you about quantum matter without quasi-particles, some simple examples. And as considered as quantum system, these have the property that many body levels, energy levels, cannot be written in terms of single particle levels, even after including interactions. And thermalization and chaos have a time limit. They cannot happen faster than Planck's constant divided by temperature. And these two very basic properties are also properties essentially of all black holes. So, thank you.
Thank you for this interesting talk. Are there any questions?
Yes, Marla.
Do you get a microparticle that looks like what you would hope for?
Sure. I mean, I showed you a picture of it, right? The entropy just is an entropy of all this entanglement that I showed you right here. It's all this motion that gives you all that entropy. That's the entropy. So there's a little small region with electrons all entangling with each other, and that region turns out to have a dual description of the theory of gravity in one higher dimension.
The analytical theory, how does that work?
So analytically, many properties of this model and gravity and anti-de Sitter space do match precisely. Okay, I have to. It's a statement that requires careful. There's a precise statement which I can tell you a bit more later. But in particular, it's not really the entropy itself. We cannot compute from gravity because that's a free parameter in gravity. It's a temperature derivative of the entropy that matches perfectly. Okay. Yeah.
Is there an intuitive way to motivate the t-squared dependence of the critical temperature for the pairwise?
T squared, you mean for the quasi-particle case? That's for the Fermi liquid. Oh yeah, that's very simple. That just comes from Fermi's golden rule. So this T squared here.
No, I'm sorry. Not forward again. The t-squared over threshold.
Little T squared.
Yeah.
Yes. That is a little subtle. It's not something I can just do without doing a little bit of. It's simple enough, but it does require you to know this result. It requires you to know this 1 over square root of time result here, and then it's a consequence of that.
That's what you glided by.
Right. Yeah. Yes. Well, no. So this behavior is by no means, believe it or not, this is the only system where we know how to do this calculation. Where we can actually plot many body levels, just looking at the levels tell you there's no quasi-particle. It's yes, yeah. Sure. I mean, this is calculating. That's not a completely trivial calculation. It's required, but that as I mentioned, I had this other Ising model, which looks simpler, but it's not solvable. So basically, what happens is that if you can solve a many-body system, or as we say, if it is integrable, it will not thermalize quickly. It will have quasi-particles by definition because of just the way. That's what makes it easy to solve, because it's got this decomposition into single particle states in some complicated way. And this model is sort of like the Goldilocks model. It's simple enough I can solve it, but still complex enough where I can actually do this calculation very easily. And there's really not, I don't know of anything else. Yeah. Sure. Yeah, I mean, for the super Yang-Mills, there's a huge literature on such things. Yeah, there's a operator field correspondence with the two sides of duality. I think for the Syk, there is some understanding of that, but certainly not at the level of the AD and CFT correspondence. People are just, yeah, I would say there's not much understanding of that. People understand things like energy and density, what the correspondence is on the two sides. But beyond that, it's still a bit of a black box. Yeah. Fair enough. But we live in a universe with strange metals. Yeah. Okay. Well, just as a disclaimer, I say I am a condensed matter theorist, and I don't really care about the universe. I care about strange metals. But no, this is just so that I don't want to. But there are many people who care about the universe who yes, who worry about precisely these issues. And of course, they would love to have a model that can describe an evaporating black hole or the expanding universe and describe it as a quantum system on the boundary. I don't think anyone knows how to do it. And one of the reasons we can't do it is because these, considered as quantum systems, these are systems that are completely out of equilibrium. You know, black hole is evaporating forever, universe is expanding. The unique feature of anti-de Sitter space is the black hole doesn't evaporate. It's an eternal black hole. It's always there. So it's in equilibrium and it's eternal. So once things are stationary and eternal, they become a lot easier to deal with. So that's one answer. That's why we are able to make progress. The second answer is that many of the deep questions in gravity having to do with where does this entropy come from, what about the information paradox, where does the information that goes in the black hole when you can certainly do things like change the degrees of freedom on the boundary and the black hole will increase in size or something. You can certainly talk about non-equilibrium questions. You can talk about throwing things in the black hole and seeing where the information goes. So these are questions that people are now answering and making a lot of progress on, not me personally. And these are all questions that can be addressed also in anti-de Sitter space. They have analogs. So all the difficulties, the conceptual difficulties of, does quantum mechanics break down near a black hole that Hawking proposed in '75, all of his arguments apply without change to anti-de Sitter space too. And at least in the case of anti-de Sitter space, we can explore those questions. But Katrin, did I answer that okay? Well, by finding the black hole dual and solving Einstein's equation, I mean, that's one way, but it's not easy. So, I mean, that is precisely the question that keeps me up at night, but. Right. So, I mean, that question is exactly what we're trying to figure out in a strange metal. What do I replace the Boltzmann equation by? So the history of the subject is that for certain theories, like super Yang mills and now the Syk model, some of those questions have gravitational analog answers, but in a higher dimensional space and of no use to experimentalists really. But I think what's been happening in the last year or two, is that now that we understand so much more about the Syk model, people are solving models like this. And for models like this, we are starting to get an intuitive picture of what's going on. And this is, in fact, what my group is working on intensively. Models like this of different flavors and solving them and understanding in the hope of finally making first of all, understanding existing experiment where there's no shortage, but maybe even making some predictions. We'll see.